Hi, my awesome neurobiology classmates. This is Ian Haight, and I'm going to give you a short presentation on what I'm calling lending a hand to those in need, neural control of prosthetic limbs in adults and children. Since we were meant to conduct research on something to do with either prosthetics or neuroplasticity, I was actually interested in kind of how both of these integrate into how prosthetic limbs are essentially wired into our nervous system. I'm first going to talk to you about this paper on the bottom here, which is a review paper of just how prosthetic limbs work in general. Lots of good information there. And then I'll dive into more specifics on this paper here, which is a very recent research paper on prosthetic limbs in children and sort of just looking at a particular model that they explain. So amputations or loss of limb occurs for a variety of reasons. It could be an accident, combat, various infections, gangrenous stuff, diabetes, which cuts off circulation to the extremities, cancers like tumor removal, and I hadn't thought about paralysis, which technically shouldn't fall under amputation, but prosthetics are often used to address paralysis. Usually these are the most extreme cases. Prosthetic limbs come in sort of two general categories. The first is just body-powered prosthetics. These are your simplest ones. This is like sort of the rubber hand or a hook. They can at most have some motion that's based on motion of the limb. So you'll often see these, there's a picture here, that have some kind of like shoulder strap and a wire coming out of it so that when the arm is extended, the gripper is sort of open or close, but pretty simple. Robotic prosthetics are where we get a little bit fancier. They can have built-in motors that respond to limb motion, sort of similar to the body-powered ones, but there's also phone apps, physical remotes. But what I'm most interested in is ones that are wired into the nervous system and can actually, in some cases, reflect the user's intent. If they want to move a finger, then a finger actually moves. So the way this works is by having interfaces with the nervous system, and so it's usually done with electrodes. This comes in sort of three general categories. Myoelectric systems, very similar to what we've been learning about with EEGs. It's essentially sensors placed on the surface of the skin, often over muscles or things like that, and they just pick up literally surface level electronic stimulation from the nervous system and then trigger some kind of movement. So not entirely accurate, and often these are put on any remaining muscle. So after an amputation, sometimes there's a little bit of muscle left. Sensors can be put on those, and then the users just have to learn to flex those muscles to cause something like a finger or hand or grip movement to happen. Peripheral nerve electrodes, so the con to this is that these aren't very specific, and you have to replace them every day, you have to calibrate them every day. Peripheral nerve electrodes, this is where you actually have implants, and it's done in two different ways. You can have a cuff, which is basically placed around a collection of nerve bundle. That's sort of more external, or you can literally have internal innervations. And these are especially effective in muscle. The one challenge is that muscle is often contracting, and so it does get hard to insert these sort of electrodes into some muscles, but there's been, if you think about pacemakers with hearts, there's been some success there. But the problem is that with any implant, you're going to have an immune response, and often the way the body responds is by walling off these sensors, and then they are not as effective. So these aren't very long lasting. And the most extreme cases are the brain-computer interfacing strategies. This is often used for things like paralysis, where you have complete loss of both legs or something like that. And again, it could be an EEG that's external, not the most efficient thing, but often sometimes you'll literally have sensors placed over part of the brain, like the motor control region, literally inserted in the space, the connective tissue between the skull and the brain. But again, don't last very long. It breaks the blood-brain barrier, so there's a much higher risk of infection and other issues. And I'll emphasize too, and I'll be kind of bringing this up, is this idea of 3D printing has sort of been a big breakthrough in a lot of these innovating technologies. Now, I was tempted to look into a lot of those different things, but honestly what came to my mind is, what about prosthetics for children? What's being done for young ages? And the issue, it turns out, is that not a lot of prosthetics are made for children. They're mostly made for adults. There's very few companies that scale down their prosthetics. It's expensive. They don't see it as worthwhile. But it's actually hugely important because, as we've been learning about brain plasticity, a lot of children establish their proprioception, their posture, their movements and habits at a very young age. And so if they're not using prosthetics at that young age, it becomes very hard for them later in life to then learn how to use prosthetics. And so using prosthetics when they're younger, even simple ones, can ease the transition into using adult prosthetics and fancier ones in the future. And there's also sort of an issue with cost. I had no idea, but prosthetics cost between $3,000 and $20,000 or higher. Not very accessible in low-income countries, but again, the advent of 3D printing has definitely reduced the cost and increased accessibility across the world. So, in terms of looking at prosthetic limbs for children, particularly toddlers, I wanted to talk about the soft grasp infant myoelectric prosthetic arm, also called SIMPA, which I guess sounds better than SIGIMPA. They left the G out of the grasp there. It has 3D printed parts that are personalized and augmented, so you can see here the cuff. They can just sort of scan the stump on the particular child and then create a customized cuff, and they don't have to use plaster cast or anything like that. It can all be done digitally. You can see here that there are 2 fingers that have 2 joints, three parts, and then a thumb that just has 1 joint, 2 parts there in the middle. It's made out of 2 different materials. This dragon skin 30 stuff is sort of softer and is good for gripping. And then this smooth sill stuff here is a little more rigid, and so it allows the fingers to sort of bend and then move back into their original position. And you can see that there are wires, tensile wires running through these. That's what they're operating on. So there's a little motor on the inside of the arm here. It has a battery that lasts anywhere from 6 to 33 hours depending on the amount of use. This costs about $600, making it much more accessible. It weighs about 395 grams, which they say is not much heavier than the average infant arm. And all of these parts are replaceable so that they can be switched out as the child grows, which I thought was pretty cool. And it all works on this, what's called an SEMG armband, and that's what I want to talk to you about a little more. SEMG stands for surface electromyography, and it's basically just like an EEG. What they're using for this particular device is a voluntary opening single-site SEMG control, which I thought was kind of funny. They call it the cookie crusher. It's apparently one of the simplest myoelectric mechanisms. It literally just sends one command. It's binary, as you can see here. And so, in this case, it would literally just be sort of an open-close control. The sensor is placed right over the bicep muscle, so this is assuming that there isn't enough left of the forearm, that the forearm's mostly gone, and so this is placed over the bicep. And so here you can see they tested, here are 4 flexes of the bicep muscle that you can see, and read by this SEMG. And then in the device itself, here are sort of the 4 binary responses. And if you can see, it's done over a time period of 10 seconds, and they pretty much match pretty well that when the muscle was flexed, there was a response in the sort of Arduino device that's inside the arm. And the binary, sort of the high-level stimulation, that's going to open the little finger clasp, and then the 0, the resting, is in a closed position. But you can kind of see here there is a lot of noise. Again, it's a surface; it's just on the surface of the skin, so there's it's not very specific. And also, they're saying that in children in particular, it's probably going to have to require a lot of low sensitivity. This was tested on an adult. This was not tested on a child or a toddler, and so that research, they say, still needs to be done. And then I just thought this was really interesting. They do what are called grasp tests, where they just try to test out different objects. You can see they have like a little squishy ball or a toy, which again is something that a child would be playing with more, or more importantly, something like a water bottle that's kind of useful. And interesting to see that it could handle the weight. So you can see here they have the empty plastic bottle and then the full water bottle. And in both cases, there was 100% success in grasping and being able to handle those. And what these, just due to the simplicity of this sort of hand structure here, you can see that the lowest numbers were with the cone and the pyramid, and probably just because it kept falling out easily, or couldn't get good enough grip on a certain side of it. But overall, on average, it was about 87% success rate with the 3-segmented thumb, 82% success rate with the 2-segmented thumb, and then they decided this was the one to go with. They emphasized that it was more sort of visually appealing, which I thought was funny. So looking to the future, there's a lot of great things happening in Good Hope. There's huge advancements in EEG and EMG. These sensors are getting really fancy. They also now have some that can be implanted directly deeper into muscles, and then they wirelessly transmit signals from the muscle. And now they're making ones that can be bioprinted, so these are bespoke or sort of personally made, and those are going to avoid the immune response, so they might be much longer lasting if they're made by cells that the body already recognizes. Targeted muscle innervations, this is a really cool surgery where basically severed nerves from the amputation can be rewired into muscles, oftentimes muscle that has lost its the other nerve connections. And this just means that there's more nerves that they can work with. It gives stronger singles in the muscles that can be picked up. They can use what are called hydrogels, these sort of hollow tubes that when a nerve's cut, they can insert the tube and the nerve sort of grows through that tube that then becomes the sensor. Or they can actually now create artificial muscle as well that they can then graft onto an amputee in a certain location, and it just gives them more space for sensors or more things to get readings from. So this 3D bioprinting is incredible. I didn't know much about this, but if you know how a 3D printer works, it deposits living cells on a surface just like melted plastic, and so you can create artificial muscle tissue or other sensors. And so it's going to be really groundbreaking, improve the longevity of implants, and also avoid immune responses. Thank you very much.